Okay, let's dive right in. Picture a massive, multinational retail enterprise right in the middle of a chaotic holiday rush. Maybe it's Black Friday. You've got thousands of physical registers across hundreds of stores, and they are furiously ringing up sales, processing returns, and updating inventory, all at the exact same time. If you manage retail technology, you know firsthand that this data is constantly flowing from local point-of-sale registers across all sorts of varying networks straight to your central servers. It's just a massive, chaotic stream of information. And here's the kicker. If that data isn't perfectly synchronized, the resulting financial and inventory mess could literally cost millions. So in this explainer, we're diving deep into the fascinating, highly critical world of Oracle Retail Xstore Office replication. We're going to look under the hood and see exactly how this architecture manages these wild data streams to keep enterprise systems perfectly and safely in sync.
We've got a beautifully structured roadmap for our journey today. First up, we'll cover the golden rules of replication. Then we'll explore soft ordering and why that sequence matters so much. After that, we'll meet the resequencing publisher. Then it's on to managing clusters and store IDs before we dig inside the replication database, and finally wrap things up with monitoring and system maintenance. Let's get started.
Section 1. The Golden Rules of Replication. Let's establish exactly what this system is built to achieve before we start looking at the actual code and database tables.
This foundational definition really perfectly sets the stage for our architectural blueprint. In the Xstore ecosystem, replication is specifically about taking data generated at the physical registers in the store and safely pushing it all the way up into the central Xstore Office database. Now, sure, that sounds simple on paper, but think about the real-world challenge here. You're dealing with disparate physical locations, wildly unpredictable network latency, VPN drops, and a sheer transaction volume that spikes heavily depending on the time of day. Building a system to handle all of that requires a very rigid set of operational rules.
The absolute top priority of this system, its true north, is that data must never be lost, period. Even if local registers go down, mall internet connections hiccup, or central databases momentarily fail, the architecture is designed to cache and hold on to that data until it can be safely delivered. Beyond that bulletproof reliability, the system needs to be scalable across server clusters, provide robust metrics for administrators to actually track the data flow, and preserve what we call soft ordering. We'll dig deeply into soft ordering in just a moment, but first let's talk about the philosophy behind that middle point, being reasonably performant. I want to frankly acknowledge a core system constraint here, which is brilliantly captured in this piece of source material. Reasonably performant does not imply real time. Imagine that Black Friday rush again. Extremely high loads will naturally create massive data backlogs, but the system's absolute mandate is safety over immediate speed. Think about it. If the central system tried to perfectly synchronize every single transaction in absolute real time, any central network lag would freeze the local in-store registers while they waited for a database confirmation. That is totally unacceptable for customer service. A delay in the central office? That's acceptable. Data loss or a frozen register at the checkout line? Absolutely not.
Section 2. Soft ordering. Why order matters. Let's look at a real-world retail problem that this system brilliantly solves by preserving the sequence of events.
Imagine a customer in your store makes a purchase at register 10. A few minutes later, they realize they bought the wrong size, so they walk over to the customer service desk, register 1, and immediately return that item. Well, if Xstore Office doesn't process these transactions in exact chronological order, the math completely breaks down. If the central database processes the return before it has even recorded the initial purchase, it triggers a negative inventory anomaly and completely ruins the customer's financial ledger. The system absolutely must process the purchase before the return, even though they were handled by two completely different registers, sending data packets over the network at slightly different speeds. That crucial concept is soft ordering.
So the vital takeaway here is that while the system meticulously preserves the order created within a single store, it relies entirely on the hardware timestamps generated at the local point of sale. If a specific register's internal hardware clock is physically fast, but even 2 minutes, it stamps all of its transactions with an incorrect future time. The replication system cannot inherently solve this logic puzzle. It just blindly follows the timestamps it receives. As the saying goes, garbage in, garbage out. It restores the sequence that was stamped at the store, but it doesn't have the magic ability to invent the true chronology.
Section 3. The Resequencing Publisher. This brings us to the actual hero of our data journey, the engine that sorts this all out.
Think of the resequencing publisher as a highly organized traffic cop, or maybe a meticulous mail sorter working at hyperspeed.
Because data packets from various registers arrive at the central server completely out of order due to network routing, the publisher gathers all incoming replication objects and strictly groups them by their store IDs. This step is critical. If it didn't partition the data by store, you'd have multiple processing threads stepping on each other's toes, creating massive race conditions and database deadlocks. Once grouped, it sorts them by their original timestamp before permanently writing them to the disk.
And the way it manages the chaos of network latency is pretty brilliant. It uses a configurable time delay to grant a mathematical tolerance window. Let's look at a concrete example. Say it's 10:05 a.m., and your delay is set to 5 minutes. The publisher is currently only processing and saving data stamped at 10 a.m. or earlier. It intentionally waits. If a purchase packet stamped at 9:59 a.m. just arrived late because of a spotty network connection, the system hasn't moved past that time block yet. The late packet neatly slots right into its proper sequence before the publisher saves the batch, ensuring that soft ordering promise is strictly kept.
Section 4. Managing clusters and store IDs. Let's transition into the architecture of load-balanced clusters to see how multiple Xstore Office servers collaborate without corrupting the data.
If you're running multiple central servers for high availability, you absolutely cannot have server A and server B trying to process transactions for store 100 at the exact same millisecond. That would cause massive database corruption. So, whenever a server boots up and joins the cluster, or crashes and drops out, this highly choreographed 5-step dance occurs. First, everyone is notified. Second, all servers immediately pause their publisher threads to drop any active database locks. Third, the newest server in the cluster takes charge and fetches the master list of all active store IDs. Fourth, that list is evenly divided among the active servers based on their age in the cluster. The oldest server gets the first batch of stores, the youngest gets the last. Finally, the threads restart. This logical step-by-step negotiation takes only milliseconds, but it guarantees perfectly predictable, non-overlapping workloads.
Section 5. Inside the replication database. Now let's roll up our sleeves and look at the actual configuration parameters and database tables that administrators use to tune this engine.
First off, it's vital to know that Xstore Office doesn't just dump all this incoming transaction data into its main operational database. It utilizes a separate, distinct SQL database dedicated entirely to replication. Why? Well, because the input/output operations of transient replication data are absolutely brutal. It's a continuous heavy volume of inserting, updating, and deleting. If this was merged with the main database, it would cause massive I/O bottlenecks, completely slowing down enterprise-wide reporting, management dashboards, and overall operations. Keeping them separate is a massive architectural advantage. As an administrator, you'll manage the system's heartbeat using specific properties in the xcenter.properties configuration file. Digging into these specific parameters, you can see exactly how tightly you can control your infrastructure. You dictate the resequencing delay we discussed earlier, typically setting it between 5 and 300 seconds. You control the polling interval, dictating how aggressively the system checks the queue for new objects. And crucially, you define threads per org ID. This setting dictates how much concurrent processing power is dedicated to chewing through a replication backlog. But be careful here. Setting your thread count too high might process data faster, but it could severely overload your server's CPU.
Once that data actually hits the database, it lands in a specific table called RPL_replication_data. Inside this table, every single transaction tracks its own lifecycle through a set of strict statuses. Let's follow one. A transaction enters as new. If the database save goes perfectly and it passes the data to the rest of the enterprise, it becomes complete. If a malformed packet completely fails to save, it's marked error. Or, interestingly, if it saves to the local database successfully, but the external Cloud Inventory API endpoint happens to be down, it gets marked unbroadcasted. This strict status tracking ensures absolutely nothing is ever silently dropped into the void. You, as the administrator, always know exactly where a transaction got stuck. Section 6. Monitoring and System Maintenance. For our final section, let's look at how we maintain this database and give Tier 3 support the tools they need to keep an eye on its overall health. We have to remember the transient nature of the system. This replication database is not a permanent archive. It is a high-speed processing funnel. Because the table sees constant heavy inserting and eventually clearing out, running vendor-specific SQL scripts daily is an absolute non-negotiable requirement for stability. These scripts rebuild fragmented indexes and run a crucial cleanup job, automatically deleting any record marked complete that is more than 3 days old. The stakes here are incredibly high. If those cleanup scripts fail to run, the database tables will rapidly bloat, indexes will shatter, performance will grind to a halt, and replication will eventually crash.
But hey, when things do go wrong, say a batch of error statuses suddenly pops up, you don't have to just blindly write database queries to figure it out. Through the Support Tools menu in Xstore Office, you get this incredibly clean graphical interface called the Replication status page. You can easily search for failures by store number and view the exact Java stack trace. For your Tier 3 support team, that stack trace is gold. It shows the exact line of code where a data packet tripped up, allowing for rapid debugging. And once the underlying network or data issue is fixed, you can manually trigger a reprocess command right from the interface with a single click to push the backlog through.
We have covered a massive amount of technical ground in this explainer, from the rigid rules of data safety and the vital importance of soft ordering, all the way to the elegant cluster sharing dances of the resequencing publisher and granular database properties. But since hardware timestamps are the absolute, undeniable lifeblood of chronological soft ordering, I'll leave you with this critical question to take back to your own infrastructure. Are your in-store physical register clocks tightly synchronized via a time server? And are your polling delays truly optimized for your specific network's reality? Think about it, because as we've seen, this replication architecture is incredibly robust and scalable, but it relies completely on the accuracy of the data you feed it. Thanks for joining me on this deep dive. Go check your server configurations, ensure your store clocks are synced, and keep learning.